live. So hello, thank you very much for being here. We're very happy to restart our new season of Latin American webinars on physics. Today we have Pellegrino Piantadosi from NYU Abu Dhabi. So Pellegrino finished his PhD beginning of this year in Bologna. In Bologna? Yes.
Yeah.
And since then, he joined our group in NYU Abu Dhabi, and we are very happy to have him here today with us. So Pellegrino will describe his recent work on rediscovering the standard model with AI. So please, the floor is all yours.
Yes, let me just share my screen.
Perfect.
Okay, can you see? It's
Yeah.
full screen, right?
Yes, perfect.
Okay. Yes, I want to thank all the organizers for the opportunity to present my work. And in particular, I want to thank the host for the kind invitation. And yes, as Nicolas was saying, what I'm going to talk about today is based on a recent work I did in collaboration with Fernando Quevedo and a graduate student, Aya Abdelak. And yeah, this is the archive number. And yeah, as you can see from the title, it is about the application of artificial intelligence and in particular unsupervised machine learning in the context of particle physics. Yes, let me just start by giving you some motivations for our work. As we know, machine learning is going to be an important tool in science and also in physics. And yeah, so it is crucial for us to establish whether a machine would be able to reconstruct what we already know about the standard model as our most fundamental theory at the moment. And in particular, we are interested in see whether the machine is able to reproduce the capability of the standard model into classifying particles in families like baryons, mesons, leptons, and so on. And in literature, there are actually works on in this line, also in other fields, like in chemistry, where people have been trying to reconstruct the periodic table of the chemistry by using unsupervised machine learning applied to data regarding the chemical compounds. And so it's natural to ask, why not try to do the same in the case of particle physics? There are actually some attempts in which people are trying to reproduce more formal aspects of the standard model, like the gauge structure of the Lagrangian by using symbolic regression. But in our opinion, the very first step in the learning procedure and also in the discovering process is the observation of conserved quantities like the charges of the standard model. So the idea of our work is to see whether the machine is able to reproduce the theoretical aspects of the standard model by giving to the machine as inputs just the experimental data, so without any theoretical input, and see, in other words, if the machine is able to do the theory job for us. And yes, what I'm going to use are very widely used method in unsupervised machine learning. For instance, dimensionality reduction methods and clustering. I'm going to quickly review these methods for those who are not familiar with these techniques. But yeah, before doing that, let me just giving you an example on how we can extract physics information just looking at the data. For example, we can consider this very simple plot of the mass versus the lifetime for the most common particles. And we can see, just looking at this kind of scattering, that we can distinguish two clusters in terms of lifetime. in particular, we have this cluster here for particles with a lifetime of order of 10 to the minus 21, 22 seconds. And these are those particles which decay mainly through the strong interaction. Whereas in this other case, we have another clusters for those particles who have a lifetime of order of 10 to the minus 9 or larger seconds. And these are the particles which decay through the weak interaction, so for which the decays are slower and more rare. And yeah, then one can also look for outliers in this kind of plot. For instance, we can see that there are at least 3 particles in the middle region. In this case, we have pi 0, eta, and sigma 0. And actually, these are particles which interact mainly through the electromagnetic interaction. Then we can see also that there is the neutron, which has a lifetime, which is larger, much larger, order of 10 to the 3 seconds. Yeah, but this is just because of the very small mass difference with respect to the proton. And yes, then instead, if we look at the mass, we can see that at least for these particles, which are the light ones, we can see that all the baryons, because the color here is for the baryon number, so the blue is for the mesons and the orange for the baryons. And we see that in terms of mass, all the hadrons with all the baryons have a mass which is equal or larger than the neutron one, whereas the mesons have a smaller mass. So yeah, this is just to give you an idea on how just looking at the data we can extract interesting physics information. Of course, if we want to get something deeper, we need to look at other kind of data. But actually, we have a lot of experimental data for the particles. For example, in the case of the decay modes of the particles, the problem in this case is that if we want to construct a data set using the decay modes, then we will end up with a very large data set. So we need to figure out how we can manage this kind of data. And in this sense, machine learning can help us, because in the case of unsupervised machine learning, we have a subset of techniques which are called dimensionality reduction methods, which allows us to reduce the dimensionality of the data, so it becomes much more easier to deal with very large data sets, and also to try to give an interpretation of the distribution that we see when we plot them. So, of course, if we want to use machine learning, we also need to figure out how we can provide the data to the machine. So we need to construct somehow a data frame, which would be the input for the machine. And in the case of the data regarding the decay modes, we can do something like this. So we can consider a matrix in which we put particles as rows and particles as columns. And for each row particle, we can look at the corresponding decay modes and also to the decay products inside a single decay mode. And then we can put as entry of the matrix 1 or 0, whether the particle product, the column particles appears as one of the possible decay product for the row particles. So yeah, just for giving an example, in this case, we have the decay process for the pi plus in muon and neutrino, muon neutrino. So in this case, we will have 1 for the corresponding column, and all the other entries will be 0. Okay, so the same for all the other particle in the rows. And if we do something like this, of course, okay, here we have a binary entry for the matrix. Then we can be also more sophisticated, and instead of put 1 and 0, we can consider the corresponding branching fraction for the decay process. And in this way, we also get a natural normalization for the single row. Otherwise, we need to think about a different kind of normalization in order to not give more importance to those particles which have more decay modes than the others. And yes, but the problem is that when we do something like this, of course, we will end up with a very large matrix of order of, let's say, 1,000 rows cross 1,000 columns. And most of the entries of the matrix will be 0. So there will be a lot of redundancies, and we do not want to manage such a large data sets, even because we want to, at some point, visualize the data, and so we need to reduce the dimensionality of this data frame. And yeah, in this sense, we can adopt the dimensionality reduction methods. We can distinguish the linear methods from the nonlinear ones. The most commonly used linear dimensionality reduction method is principal component analysis. This is based on a statistical approach, and the main idea is to try to preserve the variance of the dataset when we go to a lower dimensional space. And we can do something like this, looking at the covariant metrics for the datasets, or if you want, for the standardized dataset, so centered with respect to the mean and normalized with respect to the standard deviation, and then search for the corresponding eigenvectors. Then we can also order the eigenvectors in according to the corresponding eigenvalue. So we know that all the eigenvalues will be positive, and the eigenvectors which corresponds to highest values in the for the eigenvalue will correspond to those eigenvectors which captures most of the variance of the dataset. So basically what we are doing in considering the eigenvector is just a linear combination of our original variables in such a way that we get uncorrelated new variables, and the first ones will be the ones most important in order to keep the information regarding the variance of the dataset. And so we can just keep the first, let's say, k components and project our dataset on this new lower dimensional space, doing something like this, where the matrix Vk in this case is just the matrix that we would get considering the first k eigenvectors. The problem here is that in this case, we are just looking at the global features of the dataset in terms of covariance. But if we want to preserve also the local structure among 2 points in the higher dimensional space, we need to look for other kinds of methods, the so-called nonlinear ones. In our work, we consider the distributed stochastic neighbor embedding. It's a very complicated name, but the idea is relatively simple. We want to use this method in order to preserve the local structure of the dataset. So if we have a distribution in the original space, and if we have 2 points that are very close, we want to preserve the probability of these 2 points to be close also in the lower dimensional embedding. And yes, this can be done using a probabilistic approach. So in this case, if we consider the higher dimensional space, we can introduce a conditional probability in terms of a Gaussian-like distribution, which will be the probability for 2 points to be close in the higher dimensional space. And then, of course, we need to symmetrize this conditional probability in order to get a joint distribution. And once we do this for the higher dimensional space, where the variables are denoted as xi in this case, then we need to do something similar for the lower dimensional embedding. And in this case, we will have new variables. Here, I'm denoting them with yi. And in principle, we can consider a distribution in terms of Gaussian function also in this case. The problem is that when we do the dimensionality reduction, there is the tendency of the dataset to put much more closer because of the compression of the data, of the space, we have the tendency of having particles with points which are much more closer than they should be. So instead of using a Gaussian-like distribution, it makes much more sense to consider the student t-distribution, because in this case, we will have heavier tails, which will keep well-separated points that are far apart in high dimensional space. So once we manage to get these two distribution for the two spaces, then we can ask for the lower banding to have a distribution which is as closer as possible to the original one. And this can be done just as asking for the minimization of the divergence between these two distributions. So we will search for those y variables which are such that this divergence is minimal. And in this way, we are sure that we are keeping as much as possible the local structure in the higher dimensional space. Okay, so the dimensionality reduction methods can help us in trying to reduce the dimensionality in order to visualize the data. For example, if we want to reduce the dimensionality to be 2 or 3 in order to plot them. But then we also need to look at possible clustering, which can describe similarity between the particles in our case. And there are several methods in unsupervised machine learning. The most widely used is the so-called k-means. In this case, this is based on the idea that we can construct clusters by using an algorithm in which we define first the centers of the clusters as randomly points. We need to specify in advance the number of clusters that we want. And then for each point in our dataset, we measure the distance in terms of within cluster sum of squares. So a distance defined in this way. And then we try to minimize this distance, which is the distance of our points in the higher dimensional space or in the lower dimensionality reduction one. And we look for the distance with respect to the closest cluster center, and then trying to minimize this distance and define new clusters according to this distance. We will end up with, the algorithm can converge, and we will end up with a certain number of clusters. And then once we get the clusters, we can also look for the quality of this kind of clustering, introducing some kind of scores, something like this ratio, for example, for each point. Then if we sum with respect to I and we divide it by n, we get a single score value. And according to the value of this kind of score, we can establish whether the clustering is good or not. For example, in this case, if we get a score which is close to 1, it means that we are getting a good clustering in the sense that the clusters are very well separated, whereas values which are of order of 0, then it means that we are getting an overlap between the clusters, so it's not a good clustering. Okay, then if we are getting negative values, it means that we do get clusters, but they are not the right ones. An alternative way for clustering is the so-called hierarchical cluster method. And yeah, this is something similar, but the main difference is that we do not need to specify the number of clusters. In this case, each point, we start with each point to be its own cluster, and then we develop an algorithm in which we compute the within cluster variance, and at each step in the algorithm, we merge the closest pairs in order to end up at the end with a unique big clusters. So we have an iteration in the clustering, and according to the level, we have different clusterings. And I mean, the last one will be just a single big cluster. So the closeness between the clusters can be computed in this case using the so-called word method. And basically it's just the idea to minimize the total near cluster variance. And yeah, in this way, we will get a different approach. But the advantage in this case is that, as I was saying, we do not need to specify in advance the number of clusters that we want. And we are also able to look at substructures in the clustering. Okay, these are the tools that we need in order to analyze our particle data. And yes, now we can just use them in order to get the results we're interested in. If you remember, I was talking about the problem of having a very large matrix in the decay modes data frame. So it makes sense in this case to use the principal component analysis, so the linear dimensionality reduction method, because yeah, I was saying that most of the entries will be 0, and we want to get rid of those columns which do not apport as much information as we need. And once we apply the principal component analysis and we project our data set to the plane made by the first two components, we will get something like this for the particles. And here the color is again for the baryon number, the modulus of the baryon number. And even though we do not get two different clusters, we see that there is a separation in terms of the baryon number. So if you want, we are able to distinguish the baryons and the mesons according to a roughly straight line. In the upper side of the plot, we have the mesons, in the lower one, the baryons. And this actually works quite well, except for 2 points, 2 baryons, which actually corresponds to the proton and neutron, for which, of course, the decay modes process does not work well because of their relativity stability. And yes, we can try to do something similar, but a bit different. Instead of considering just the first decay processes, we can consider the full chain. And if we do something like this, and again, we apply principal component analysis, this is the plot that we would get. So in this case, we actually get a split in the baryon number. So again, we can distinguish the baryon from, so the red ones from the mesons, the green one. But in this case, the machine is also able to separate the baryons from the antibaryons. So somehow the machine is able to see the sign, the actual sign of the baryon number, not just the modulus. And yeah, this is what we get on the left. The right is the same plot. It's just a zoom in the central dense region. And we see that, I mean, it's still true that we have the separation. And we can also notice that we have these kind of lines, but the reason for this is the fact that we are considering the full chain of the decay modes. So the particle in the center of the plot will be likely the lightest ones, because they will be the, say, the common decay products of all the other particles. So this is just to justify the shape of this kind of plot. Okay, so if we look just at the decay modes, in particular in terms of the decay products, we are able to get information regarding the baryon meson classification and also the baryon number. But then if we want to get something else, we need to look at other data. And another natural generalization of the mass versus the lifetime plot would be the inclusion of the spin. The spin is something that can be measured, so we are allowed to give this information to the machine according to our idea of only considering experimental data. And if we consider spin, mass, and lifetime, we only have three features, so it doesn't make sense to consider the linear dimensionality reduction because I mean the dimension is already small. But it makes sense to look for non-trivial relations among these three variables. So we can still use nonlinear dimensional methods. And if we apply TSNE, we can also think of reproducing the full path in the particle discovering. So we can just restricting the analysis to the light particles. Let's say the ones we know are made by up and down quarks. And if we do something like this and we apply TSNE, then what we get is a plot like this. So even though we have a very restricted number of particles, we still see some kind of clustering. In particular, if we look at the proton, we see that it is clustered together with the neutron, at least qualitatively. But the same is true for the pions, the deltas, and the rho particles. So basically what we are getting here are clusters corresponding to the SU2 isospin multiplets. And so one could say that this is kind of expected because they could be clustered according to the spin, just because of the spin. But actually this is not the case because, okay, in this plot I'm also including the leptons. So if this is due just to the spin, they should be clustered together with the proton and neutron, but this is not what's happening. So I mean, the machine is able to see the nonlinear relation between the three variables that we are giving as input. Okay, then the next step would be to include into the analysis also the particles with non-zero strange quantum number. And yes, if we do something like, if we do the same analysis, so again, TSNE analysis, and we project the data on the first two lower dimensional space components, we get, again, some clusters. We can search for the proton and neutron. We see that they are still together, but now they are clustered together also with the lambda, the sigma, and the xi particles. So then we can also look at the pions, and now the pions are together with the counts, the eta and the eta prime. So basically here we are getting the cluster corresponding to the SU3 baryon octet corresponding to the spin parity 1/2 plus. Here we are getting the meson nonet for spin parity 0 minus. And actually the same is true for the other two clusters here. This one is the other meson nonet for spin parity 1 minus, and this is the baryon decuplet. So basically we are getting clusters according to the Eightfold Way. I'm putting this as just reference for that, these two structures. And I want to stress here, and also regarding the leptons, we do not get a single cluster for all the leptons, but at least the lightest ones, so the electrons and the neutrinos, are together. But the same is not true for the taus and the muons. But this is because we are giving to the machine also the mass as input. So somehow the mass see the hierarchy in the masses, and that's why they cannot be clustered together. I want to stress here that this is the result that we get when we apply dimensionality reduction, but actually the same result can be obtained considering the unsupervised clustering. Indeed, here the color is for the cluster labels for the k-means algorithm, and it actually corresponds to the cluster that we can visualize using this dimensionality reduction. And yes, so I would say it's a quite not trivial result, and it's also quite promising because it means that the machine is able to learn the relation in terms of SU3 representations. Yes, but I was saying before that an alternative way to cluster is by using the hierarchical clustering. In this case, this is the kind of representation for this kind of clusters. It's a tree-like structure in which at each step we have different level in clustering. So the last one would be the single very big clusters, whereas the first one is the single cluster corresponding to the single particle. And the first not trivial structure in clustering is the yellow one and corresponds to the SU2 isospin symmetry. Indeed, if we look in this case, we have the first cluster, which corresponds to the cluster of proton and neutron, the same for psi particles, lambdas, and sigmas. And the second not trivial clusters corresponds to the SU3 multiplets. So like before, we are getting the cluster according to the SU3 multiplets. But in this case, we get together the two classifications. And if we combine the two clusters, we are able also to get information about the strange quantum number, because we can distinguish particle with a non-zero strange quantum number with respect to the ones which have no strange quark. Okay, so then the natural next step would be to include in the analysis also the heavy particles. So the ones we know are made by also other quarks like the charm and the bottom. And from the theoretical point of view, we would expect to get, again, some multiplets, but corresponding in this case to these kind of decompositions. So in the case of the baryons, we would expect to get a multiplet made by 20 particles, whereas in the case of the mesons, we would expect at least 15 particles. So if we want to extend the Eightfold Way to the SU4 flavor symmetry, we know that we would expect to get the structure like this. So the first layer would be the ones corresponding to the usual SU3, and then we will get other layers corresponding to non-zero values in the charm quantum number. Okay, so we can try something like this and do the analysis, including also the heavy particles. And again, if we search for the proton cluster, here we get again just the SU3 cluster. And yes, the charm counterpart would be is here. So of course, it's not grouped together. And yes, but if you want, the reason for that is that the SU4 flavor symmetry is not a good symmetry of the standard model, in the sense that is a very approximated symmetry because of the mass of the charm quark, which is much closer to the QCD scale. So it is a broken symmetry, and if you want, the machine see the break of this symmetry. That's why we do not get clusters according to the SU4 multiplets. But even though we do not get the expected clusters, we still get something, because if we look at the charm particles, we see that they are actually clustered together. And in this plot, I'm also including the bottom quark, the bottom particles, and also for them, we see that there is the same clusters. So we do not get the SU4 multiplets representation, but we do get cluster according to the charm and the bottom quantum numbers. So yeah, just to summarize what we got so far, by applying dimensionality reduction and clustering to the spin mass and lifetime, we are able to get the classification in terms of SU2 isospin and SU3 flavor multiplets, and also information regarding the strange quantum number and also about charm and bottom quantum numbers. Okay, so what we saw so far are the results that we get when we consider in the analysis the particles that are which have different quark structures. But then the next question is what we can say about particles which share the same structure. So for particles for which we would expect to see some kind of similarity. In other words, we want to study, we want to analyze the data regarding particles which are excitation of a same ground state, let's say. From the theoretical point of view, we know that the relationship between the excitation is described in terms of the Regge theory for the complex scattering amplitudes. And according to this theory, we know that if we consider a Regge family, so a family made by all the excitation of the same ground state, we would expect to have a linear relation between the total angular momentum and the mass squared. In particular, we know that there is a leading Regge trajectory in the total angular momentum versus mass squared plane. And then we can also have parallel trajectory corresponding to radial excitation in the particle wave function or corresponding to spin orbit splitting. And we want to see if the machine is able to see this aspect of the standard model. Okay, so we can think to do something similar to what we did before. We can give to the machine the data regarding the decay modes for the excitation and see what happens if we apply dimensionality reduction to this data set. For simplicity, in this case, we only focus on the baryons. Also because in terms of experimental data, the situation is much more clear than it is for the mesons, because okay, there are much more observation in excitations for the baryons than we can have for the mesons. And so we can give the decay instead of the decay products in this case, we look for the decay modes. So if you remember, I was showing you the data frame, but now instead of putting particles in the columns, we can put the full decay mode. And so constructing a data frame of this kind. And if we do a principal component analysis, in this case, doesn't work very well. So it is more interesting to look for the nonlinear dimensionality reduction. And this is the result that we get. We can see that in this case, we do get three clearly separated clusters corresponding to the sigma excitation, the lambda ones, and also the psi excitation. But the clustering doesn't work in the case of nucleons and delta particles, because we see that in this case, for them, we get two different clusters, which corresponds to two different mass levels. But yeah, the main problem is that they are sharing the same clusters. There is a reason for this, actually. The fact is that, of course, the machine is blind to the distinction in delta and nucleons, so excitation of the neutron. But if you think about it, the deltas are actually can be interpreted as excitation of the neutron as well, because at the end of the day, they have the same quark structure made by U and D quarks. So in some sense, it is right to get the same cluster for delta and nucleons. Yeah, because at the end of the day, they share the same main decay mode, which is just the neutron plus the pion. And okay, then we can see that there are also some outliers, so isolated points which do not belong to any clusters. And actually, these points correspond to the ground states of the excitation. And this is because, okay, the idea is that the cluster is due to the fact that excitation of the same ground state will share the main decay mode, which corresponds to the ground state, indeed. But of course, this reasoning doesn't work for the ground state as well. So from this point of view, we would expect to get the ground state to be not clustered together with the corresponding excitations. Okay, but of course, the machine is blind to this kind of reasoning. So we can just consider the cluster that we get and try to plot them in the plane of the total angular momentum versus the mass. Okay, as a first step, we can consider just the mass and not the mass squared, because it would be more natural to plot with respect to the mass. And if we do a plot like this, we would get a kind of quadratic curves, and we can notice that this quadratic curve starts with the corresponding ground state. So a posteriori, we could associate the ground state to the corresponding excitation. Of course, this is something that we can do a posteriori, not a priori, because the machine, as we saw, doesn't see the relation of the ground state with the excitations. And the fact that we notice a quadratic behavior can suggest us to try to do a quadratic fit. Otherwise, if we want truly use machine learning methods, we can also use symbolic regression and search for which kind of relation there is between our data, because in this case, what we would get is very simple since it's just a quadratic relation. But in our case, we just did a quadratic fit. And from the quadratic fit, we also see that the linear term is negligible. So we find the linear relation between the total angular momentum and the mass squared. And in terms of this, okay, this is the corresponding plot. So the plot of J versus mass squared. And yes, from this plot, we see that in the case of the nucleons and the deltas, we do get an overlap. So somehow the machine is right in putting them in the same cluster, because actually the Regge trajectory are overlapped. And we also can see that the slope is quite the same among all the trajectory. So we do get the universal behavior in the Regge parameters, as we know from the theory. And all the trajectory will be characterized just by the intercept, which is different for each Regge family. Of course, I was telling you that from the theory, we know that we have a leading Regge trajectory corresponding to the ground state plus all the excitation, which corresponds to the lowest value in mass for a given angular momentum. But then we can also have daughter trajectories for each family. And in this case, we are not considering them. These are only the leading trajectories, but we can select them even though we do not know anything about the theory, just because for a given angular momentum, we can just select the lowest mass, the particle corresponding to the lowest mass. So yes, so in this case, by applying dimensionality reduction method, we are able to actually reproduce some part of what we know about from the Regge theory. In particular, we get the linear relation between the angular momentum and the mass squared, and also the universal behavior of the Regge slope. Okay, yes. Let me conclude. By applying unsupervised machine learning methods to particle data, we are able to actually extract physics information, theoretical information. In particular, if we apply clustering and principal component analysis to the case of decay modes of the particles, we are able to get the classification in terms of baryons and mesons, but also look for the actual value of the baryon number, so also the distinction between baryon and antibaryon. If we apply our methods to the spin, mass, and lifetime, we are able to get clusters according to the flavor multiplets, in particular according to the SU2 and SU3 multiplets. We are able to cluster together at least the lightest leptons, so electrons and neutrinos. So we do get some indication of the lepton quantum number. And as we saw, we also get clusters according to the strange, the charm, and the bottom quantum numbers. Then we have tried to apply our methods, the machine learning methods, in the case of the excitations. And as we saw, we are able to actually get Regge families, at least for most of the baryons, and also to get some expected behavior in terms of relations of angular momentum versus the mass squared in terms of Regge relation. And yes, so in this way, we are able to reconstruct some aspects of the standard model, at least the phenomenological aspects in terms of flavor symmetry and also quantum numbers classifications. And I want to stress the fact that these are all consequences of the fact that we have charge conservation encoded in the data that we provided to the machine. Of course, what we have found are things that we already know from the theory perspective, but I would say that this is the very first step. Then once we establish that the machine is able to find what we already know, then we can try to use the machine to go beyond the standard model. In particular, our analysis can be extended to more exotic states like tetra and pentaquarks, because, I mean, in principle, this can be included into the analysis, but also to see if the machine is able to say something about beyond standard model candidates, because as we saw, we are able to see the clustering, but also outliers in the plots, and try to see why we do observe some isolated points. We can give an interpretation to them, and this could help us to find some new particles, for example, or at least to see behaviors which are different from what we would expect from the standard model. And yes, then there would be other extension. I mean, as I was saying, there are other attempts in trying to reconstruct also the gauge structure of the standard model. And I mean, I think that the study in terms of flavor symmetry can be extended also to the gauge symmetry part. And in that case, would be interested to look at what the machine learning is able to say in that case. So yes, this was everything I wanted to say. And yes, thank you for the attention.
Great. Thank you very much, Pellegrino. Very interesting. So,
yeah, thank you.
Are there questions from locals here? Well, I don't see hands raised, so I have a couple of questions.
Yeah.
So I was wondering, so what you had basically so the data set includes the mass, lifetime, spin, and the decay channels, but you're not using, for instance, the branching ratios, right? So you just took all the possibilities of decays.
No, okay. In the case of the results that we had, yeah, when we do a data frame like this,
right?
We, as I was saying, we can also, okay, these have binary entries, so just 1 and 0. But actually, yeah, this is because we are considering the decay products. if we consider the decay modes, this is what we did in the case of the results in the Regge trajectory. We were having in that case not just the products, but the full decay mode. So in the case of baryons, pi plus, for instance, the first column would be the ones corresponding to both a muon and muon neutrino. And in that case, we can consider the branching ratio, because instead of putting 1, we can put the fraction, the corresponding fraction. And yeah, this would be better actually, because in this case, we can also normalize the data frame, because in this case, because it will be normalized to 1, right? And yeah, this is more appropriate actually, because in this case, we can give the same importance to all the particles, because there will be no particle which will have a sum which is larger than 1. So in this case, all the particles will be treated in the same way. And and actually this is an important thing to do in this case, because in the case of the Regge trajectories, because because the cluster is due to the fact that the excitation share the main decay mode. So the decay modes corresponding to the highest branching ratio. So it's important in this case.
Okay, see.
So as a follow-up, so I'm a bit confused, because I think at some point you mentioned that when you included the decay modes in your first kind of analysis, it didn't work so well, right?
Are you talking about the first part, which?
Yeah. So at some point, I think that you meant I might have not heard correctly, right? But what I understood is that if you replaced in your data frame the information and included the decay channels instead, the clustering wasn't done so well.
Actually, no. In this case, we did consider just 1 and 0, because if we include the branching ratio in this case, we have the problem of because in this case we need to give the same branching ratio for different products, because for example, here if we have pi plus that goes to muon and muon neutrino, since we are considering the decay products in the columns, they would have the same branching fraction. So in this case, the sum of all, summing all the row will not be normalized to 1. And so we would have this kind of problem. Actually, we can do that, but then we need to normalize in other ways. And we tried also this kind of normalization, but actually we get the same result. So it's not crucial in this case. It is more crucial in the case of the Regge trajectory. In that case, it is important to consider the branching ratio, because we are interested in the main decay processes.
Okay, so because that surprised me, right? Because here in this table, you don't know, like for instance on K plus, right? You cannot tell if it's for instance like what you have there, right? Mu plus plus neutrino, or pi plus and pi zero, right? In the data,
exactly.
The data from you, it could be mu plus and pi plus, right? Which would
exactly. That's the point. I mean, for us, it's hard to see from how the machine from just 1 and 0 can get results, because of course, I mean, the machine is not able to see the labels, so it just see 1 and 0s, and but the point is that it's able to see how these 1 and 0 are correlated to the other ones. So in the case of counts, for example, it will see a similarity because with the baryon, because both of them have 1 on the same column. and the same for all the other particles. So yes, and the point is that when we consider all the decay products, I mean, this will be a very large matrix. I mean, we will have a very large number of columns. And I mean, what is not doable for us can be doable for the machine. That's the message that I want to share with you. Yeah.
And sorry, Nicolas, if I may ask another question. So
Please.
what happens? Have you tried including the Z decays, the W decays, Higgs? Because when one thinks of standard model, okay, it's maybe my bias. I think about the electroweak sector rather than this part. I mean, it's all part of it, right? But I was wondering what happened if you have you included the Higgs, Z, the W information?
No,
Even
because
here you have mesons and baryons, but not quarks.
yeah, because okay, because at least for this first work, we were interested to look at just the particles and not the elementary ones. And yeah, because yeah, the next step, according to us, would be to try to reconstruct the standard model in terms of elementary particles. So yes, in that case, we want to look at the internal structure of the particles, and it would be crucial to look at also the decay in terms of quarks and also zeta Higgs.
So the reason that you included the electrons and neutrinos are because they are the decay products of the other ones.
In the case of electron and neutrinos, is because we were interested in to get also the lepton quantum number. We wanted to get something like that, and that's why we included also them. But in the case of yeah, the Z boson, the Higgs, we didn't want to include that because it's something that I mean, at the first step, is not experimental observable. It's not an experimental observation in the first stages. It's something that can be observed later. I mean, also historically. And I mean, we wanted to do something without looking at the elementary structure. And in the case of the leptons, the point is that they are important because all the mesons at the end of the chain of the decay process will end up in leptons. And so that was crucial in order to get clusters for the mesons, because that would be the main similarity point among them.
Super. Thank you.
Are there further questions to Pellegrino? So I have one. So
Yeah.
for instance, you say that you put masses and yeah, okay, masses. For neutrinos, you took, I imagine, zero mass, right?
Yes, for the neutrinos, yes.
Something change if you put a small mass, or if you want to distinguish between Dirac or Majorana, or at this level is blind, right? I imagine.
This level is blind because, I mean, what is important is the scale, and so the order of magnitude. And yeah, I mean, for the machine is zero. The point is that when we consider also the other particles, it is important the hierarchy among the masses. So even though we put a very small mass, it will be interpreted as zero by the machine.
Okay, yeah, that's true.
I mean, we could
And I
do
was wondering,
this
suppose.
we
sorry,
could
please.
do this kind of analysis if we restrict it just to the light particles. I mean, with very small mass. In that case, it will make sense to give also a non-zero mass for the neutrinos. So without considering the heavy one, yeah.
And if you do exercise of, suppose you forget on purpose one of the particles, do you think it's possible to realize that there's something missing?
Yes. I would say so, because okay, yeah, this is the other way in which we are trying to extend this work. And because, okay, when we do the analysis in terms of, I don't know, in terms of SU3 multiplets, here we do get the clusters corresponding to the multiplets. But I mean, we are able to say that this corresponds to the SU3 multiplets because we know this from the theory. In principle, this is the extension we're working now. We would like to get the actual symmetry just, I mean, we would like to the machine to learn the fact that this is actually the multiplet corresponding to the SU3 symmetry. So somehow we want to try to get the generator of the symmetry just looking at the data. So in such a way, we can say that this is actually SU2 symmetry without, because we are seeing that by hand. I mean, we see the clusters, and because we know that these are the SU3 multiplets, we are able to say that these are the clusters according to the flavor multiplets. But we would like to learn the symmetry using the machine. And in that case, we could also be able to learn the representation. And so we could be able to see that fact that a particle would be missing just because we do not get the expected number of particles corresponding to that representation. So yeah, something like was, yeah, the same that has been done in terms of Eightfold Way when they discovered the omega minus. We could do something like this if we are able to learn the symmetry and the corresponding representation. So at this level, we are not able to say that something is missing, but in the extension that we are doing, in principle, we would be.
Great. Yeah, that's very exciting. Maybe a last question?
I have another one question for Pellegrino. So, I mean, there are two questions. One is because in the beginning you were mentioning that you, for the clustering, you take a specific election for the distribution, like the student T, etc.,
Yes.
etc.
Yeah.
Would you expect that another selection of this distribution or clustering technique would give you different results at some point with the, if you train again the IA with a different weighting measurement? This is the first question. And the second question that is not related with this, but is at the same time that I want to ask you to you. What about the information about the parity of the particle? Because I mean, when we used to take the data for the particle data book, when for especially for the meson, beside the spin, there is this J, if it is CP odd, CP even, etc., if it is also possible to include in the analysis.
Yes, okay. Regarding the first question, yeah, it would affect, if we choose different distribution, they would affect the results. Indeed, this is why we needed to consider the student T distribution here, because if we consider the Gaussian distribution, then we still are able to do the dimensionality reduction, but it would not, I mean, it would be worse in the sense that the cluster will be not very well separated. And this is, yeah, this is actually exactly the reason why we needed to consider a different distribution here, because otherwise, as I was saying, if we consider a Gaussian distribution, then in the lower dimensional space, the points will be much more closer than they should be. And this means that two clusters which should be separated tends to be much more closer. So the distinction between them would be not so good. In this sense, yes, according to the distribution that we consider, we can get qualitatively different results. But yes, the general picture would be the same. It would be just harder to distinguish the clusters. Yes, regarding the second question, we are not using the parity information. So this is not an input for the machine in our case. But yes, but at least in this case, we are getting clustering which are separating the particles in terms of the parity. Because as I was saying you, these are the multiplets corresponding to different spin parity. And so I would say that at least, okay, I don't know if this is just a coincidence of the fact that we all have a multiplet with 1/2 plus. We don't have the 1/2 minus in this case. But I would say that, yeah, since it's something that can be measured, maybe it can also, okay, not in this case, but when we consider, I don't know, when we include in the analysis other particles, then also the parity information could help us in getting different clusters, I would say. Yeah, but yeah, we didn't try that because we didn't provide it as input.
Thank you.
Yeah, thank you.
Okay, good. And maybe last question, I can see one in the YouTube channel. So Oscar Tuve Pavon is asking, how do you identify the decay of a baryon into 2 photons in the table if the representation is binary?
Yes, that's a good question. We do not see that, at least in this case. So when we consider just the decay products, we do not see the fact that there are 2 gammas. We just put 1. When we consider instead the decay modes, in that case it's different because in that case we distinguish the decay mode corresponding to just 1 gamma from the decay modes corresponding to 2 gammas. So in that case, we will be sensible to this difference. And yeah, but this is not the kind of data that we use for the results regarding the baryon number.
Okay, fantastic. So I think it's the moment to stop the discussion. Thank you very much again, Pellegrino. It was a pleasure to have you.
Thank you for,
very clear, very interesting.
Thank you for the invitation.
No, and we reconvene in 2 weeks or 1 week? I'm not sure anymore, guys. Help. 1 week. So next week we reconvene. Okay, for another webinar, number 185. So see you guys. Thank you very much.
Bye. See you.
Bye. Okay, finito.
Bene.
Good. Now,
Great.